The goal was to get 1 million neurons addressed singly, not an average of neurons, not 50,000 or 100,000 neurons, but a signal from each neuron, a spike train from each neuron singly. And we wanted to upload information, so we'd have a two-way path to 100,000 of those neurons. So we would have downloading the information in the brain and uploading commands. That's what DARPA solicited for. The information is all here. Next. So I don't really have enough time to go over the design. I am happy to take questions from people who want to contact me on this, but basically I proposed a design. The implanted device would be wireless. It would recharge without any external wires through an IR sensor. It would have a connection to a device like a speaker, like a smartphone on your pocket, and it would be able to download the raw or slightly pre-processed data directly from your brain into the smartphone, which could then do anything it wanted. It could continue the post-processing, it could upload it to the cloud, a lot of things that it could do from there. Everything happens in real time. The device is composed of a grid of addressable processors to carry out pre-processing of the data. It can be configured over the cortical surface, and will cover an area of about 35 centimeters squared. That's pretty big. That's like a skull cap, just so you have an idea. So it's a pretty invasive design, not even necessary anymore. In 2016, it was sort of cutting edge. So external device would do the post-processing, collect raw data. Let's keep going. Now I'm going to talk a little bit about the device itself. This is the technical part. I'm really sorry to shortchange it, but again, I'm available for questions. People have already found me to ask me questions. Just download this. Basically, it would be two symmetric mesh arrays so that it would span the brain on both sides in a symmetrical manner. We had 50 10,000 channel chips with electrodes. Each electrode was bundled as 125 micron cables with films of dissolvable material around them. They had different depths, and they were staggered over, so they were staggered in both the X and the Y direction. The dissolvable film would come off, and the electrodes would separate a little bit, but the reason they were all bound together was for the stability of penetration into the brain tissue, which, remember, is very soft, but you still don't want the thing kind of wiggling. You want it straight as you implant it. The electrode length was staggered by 2 microns, and the depth of insertion, actually, I think we're going to go a little longer than this, but the initial proposal was 500 microns. The inserted electrodes cover or fan out over that depth and gather information from neurons in something called a cortical column, which is how the neurons are organized in the cortex. Let's go. So here's sort of a cartoon. Here are the 5 electrode bundles. And then each bundle, this is wrapped up with that film that I mentioned, but it's composed of 10 varying length neurons. So you can see how the lengths vary this way and in this dimension. And each one is sort of a group for accounting purposes. And you end up with 1 million electrode probes distributed over this area. So it's sort of a sparse and distributed arrangement of these electrodes.
50 minutes.
Okay. Then each one of those hubs is arranged on the flexible material that I mentioned earlier. It could be graphene, could be silk, could be Kapton. We were looking at Kapton film for biocompatibility, but again, it could be many different materials. And this is draped directly on the neural surface. We had some way, we did have temperature probes. You cannot deviate. You don't want to cook the brain, so you don't want to deviate in energy too much. We had an automatic cutoff in a delta of 0.6 degrees so that it could cool, and the cooling was taken care of by the vascularization of the brain. Let's go. So this is just meant to be a picture. This is not ours, but this is meant to be a picture. This is a printed circuit. Ours, remember, would have the electrode sticking off of it, so this is something that sits on the surface of the brain. But you can see a huge amount of flexibility here. Again, our device would have been bigger, and again would have the electrodes, but you can see the thinness here and its ability to conform to the very deformed surface of the brain with all the sulci. Okay, so we were going to use, in conjunction with our colleagues, Hamid Krim at the University of North Carolina, something called a Granger-type causality measure. A lot of people in the audience will have heard of Granger-type causality. It has to do with looking at correlations between 2 time series of data, and from those correlations, and this is actually our data that we can look at collecting from a series of nodes throughout the brain, This would be uncorrelated data, no kidding, and this would be one kind of causal effect. This would be a different kind of pattern. From these patterns, we can determine what parts of the brain have been activated. Next. So safe implantation is mission critical. That's really obvious. You don't want it to have inflammation. You don't want it to be harmful. You don't want it to crush the brain. You don't want it to move around a lot. You have to tether it. But there's a lot of medical controls on keeping it safe. Feel free to read this. Go. The power, this is a discussion of how we're going to use the IR to power the device. And this is a little bit about electrode design. I'm just telling you so that you can look it up, but these are all links that will discuss problems and the importance of the probe tip. An impedance mismatch, for example, would cause a lot of artifacts. You don't want that. So the probe itself, the electrodes, the design is very important. Let's skip this. So let's talk for a minute about the ethics of these devices. This is a book by, I actually don't remember, some Professor Arkin, and the link is here to the book. The PDF of the book is available. You want to start thinking about the ethical basis for autonomous system deployment. This is written from the military point of view about robots, but the robots can be, and they're not exactly machined, or I'm sorry, controlled by brain-machine interfaces, although they could be. But the idea is, where are we with ethics and military devices and military uses? And I think that this is a very interesting overview because Professor Arkin is an insider with the military. It gives their perspective on this, and I think that this is an important book for people to have access to. So what's our dilemma, right? We have two things going on. I think I've outlined both of them. Their enhancement is attractive for so many reasons. There's virtual reality games. There's medical enhancements. There's quick access to the internet. There's all the world's information at your fingertips. There's communication with people who may or may not be in the room or around the planet. It's the future. It's extremely attractive. What's not discussed so much is the control it gives over the individual. If there's too much control and it's not understood, that is not attractive. So this is referring to Kahneman's book on fast and slow thinking, and I invite you all to read that as background material, but basically you want slow, reasoned thinking. You don't want to be herded into buying something or doing something or emotionally doing something without really knowing why. Do you ever notice when you're angry and you do something and later on I regret that? You don't want to do that. That's fast thinking. You want slow thinking. But in general, corporations who are marketing, or maybe the government in a war situation or not a war situation, they want fast thinking. They want you to vote a certain way. They want you to do a certain thing. They want you to buy something, right? They prefer, it's easier to understand fast thinking. It's emotional. It's quick. It's not deep. So there's a conflict here. You want the slow thinking, corporations want the fast thinking. So where are the checks and balances between these two desires, you against corporations and the government? The checks and balances, next. They were going to be in this room as I gave the talk, but instead they're in this audience. The checks and balances, oh no, go back. The checks and balances are the hacker community. We are the community of people who are going to understand how these things work, who are going to have the will and passion to take them apart, and who are going to also understand the deeper implications of privacy and of autonomy. So we are the checks and balances, and that's why I wanted to make this talk to this community. And you always want to remember, you want to be the hacker and not the hacky. So before you go out and play these virtual reality games or explore what these brain-machine interfaces are, you want to be aware of their capabilities, be aware of how they could be misused, and you want to understand and keep the code for these open source, because you want, and by you I really mean the public, we want to be the hackers and understand this, and we don't want to be the hackies and be under their control. I want to thank you all very much. Please feel free to email me. Let me know how you enjoyed this, and let me know if you have any questions. And again, thank you very much.